Hello, my name is Kafayat Hazzan. I am a PhD student at Loughborough University in the UK. I'm going to present my work entitled Crack Identification in Tungsten Carbide Using Image Processing Techniques. During this presentation, I will introduce the context for crack and defect identification, the image processing steps and algorithms used to identify cracks from SEM images, and the accuracy of the method with potential ways to improve it in the future. Advances in image processing and programming systems has allowed for the improvement of characterization in a range of applications with various types of image inputs, as the diagram shows. The techniques range from simple image calculations to complex automated learning programs. This has been mainly evident in macro crack detection in the construction industry, applied to pavements, concrete, building structures, and also industrial components such as pipelines. Each system has their respective advantages and disadvantages, but the choice is often dependent on resource availability, cost, and time. The context of this work is shown in the diagram, where SEM images are the image inputs and image processing techniques the main method of identification. The potential for using these techniques can provide an objective and cost-effective analysis of the structural integrity of components. This includes allowing for quantitative analysis of defects, which has typically been qualitative and subjective. Quantifying this data also gives room for better integration for deep learning and neural networks in entire manufacturing systems. The application of this is particularly useful in cutting tool materials such as tungsten carbide after operations like laser processing, where surface defects can be induced dependent on laser parameters. This includes balling, splatter, cracks, voids, and other defects as shown. My research aims to improve defect characterization in analyzing laser-induced damage, starting with cracks, to gain a further understanding in the laser material interaction when processing tungsten carbides. We do this by developing a crack identification method to analyze cracks in SEM images after laser processing. The diagram shows a brief overview of the stages used in this crack identification method using MATLAB. The stages utilize image processing methods rather than the use of convolutional neural networks in deep learning, as these are simpler and less computationally intensive. The image to the right shows output examples at different stages of the process. A tungsten carbide sample disk with 12% weight cobalt was selected as the workpiece, with a mean grain size of 4 microns for the laser experiment. A fiber laser was employed to laser process 1 mm squared squares on the disk using different fluence, frequency, and feed speed parameters in ambient condition, as the table shows. The samples were cleaned in an acetone solution, and scanning electron microscopy was used to view the surface topography. Multiple SEM images were taken from each process square, and a visual inspection of the images was conducted to show a range of the surface defects caused by laser processing, as discussed. The images were imported into the MATLAB workspace using the TIFF file format and converted into 8-bit images. The presentation will focus on one SEM to explain the steps used. After importing the SEM images into the workspace, it is converted to a binary image using binarization. Once converted, the image is represented as a logical array of zeros and ones. This makes the image quantifiably simpler to perform calculations and operations faster. There are various binary conversion operators, each with their own benefits, including canny, otsu, and pivot. The study used the Sobel operator as it gave the optimal results during conversion, and it's one of the more efficient operators. Its limitations are typically not a concern in the context of this work. The Sobel operator converts the input image to grayscale, computes gradients and gradient sizes as an edge detection process. Then with the use of thresholds, regions are allocated with ones and zeros to give the matrix. After the conversion to binary, it can be seen that there was noise on the image from the natural variation of the microstructure and other defects. Because these were very small compared to the cracks on the surface, the bare-welt function was used to filter this noise. This kept objects greater than 4 microns on the surface. To avoid a loss of resolution during the filtration, the pixel connectivity input variable was adapted to include pixels that not only touch in the vertical and horizontal direction, but in the diagonal as well. The diagram explains this pictorially. The remaining features are now independent from the background, and the noise is successfully filtered from the image. The remaining features were analyzed using the BW boundary function. This outlines and highlights these areas. It implements the Moore neighborhood tracing algorithm modified by Jacob's stopping criteria. The null holes input was used to give a faster process. The output of the function was analyzed for pixel continuity. There were instances where close regions were computed as separate cracks, as shown. In these situations, the regions were combined by appending the identified coordinates to one array. After doing this, the areas of the cracks were calculated using the conv function. This generates a polygon around each crack and calculates that area. The output of this method generates an array of identified crack regions. The length or number of elements in the array is equal to the number of cracks identified on the image. Within each element is an individual 2-column array containing the x and y coordinates. Each can be independently plotted or plotted on the scale of the original image. This makes it easy to view and analyze the various shapes and types of cracks present on the surface. The accuracy of the method was calculated by plotting the cracks over the SEM image. The difference in pixel value was calculated in each position. If the value of the pixel in the location is the same, the difference is 0, otherwise it's 1 or minus 1. The absolute sum and the percentage of this indicates how different the method is from the SEM image. This effectively compares the intersection points. The method was tested on a range of different SEM images processed with the laser parameters described earlier. From 49 experiments, the minimum accuracy was 95%. There were 3 types of failure modes: false positives, false negatives, and broken cracks. Broken cracks are regions where the method identified a significant portion of the crack, but failed to fully capture the ends as it gets fainter. Broken cracks were the most common failure mode, with only 39% of results having at least one false positive and 33% of results having at least one false negative. In cases where false positives were high, the method included the edges of defects such as porosity and balling as cracks. Despite the failure mode, the accuracy was still high and comparable to other studies that have been using image processing on macro cracks on concrete. Future work will include reducing these failure modes by using other image processing techniques to isolate circular features that are currently being misidentified before applying the crack identification method. This includes the circular hue transform algorithm, Upon initial testing, the method is able to identify regions of porosity and bore length consistently. Improving the broken crack failure mode will include improving the initial image contrast. The image processing techniques discussed in this presentation are very simple to replicate and use and are fast to compute. They do not require significant computational demand. The method is able to find cracks, their location, and geometry. The results show successful segmentation of cracks from SEM images with an identification accuracy greater than 95% across a range of different laser processing parameters. The achieved result shows that this process can be used for the characterization of SEM images. The authors would like to acknowledge the Manufacturing Technology Centre for funding this research and the use of the facilities in the Loughborough Materials Characterization Centre. Please contact for further information, and thank you for listening.